Hello students, let us do a very important theorem called Eulers theorem. Now what is this theorem? It states that if n is greater than or equal to 1 and GCD of a and n is 1, then a to the power phi n congruent 1 mod n. Let me remind you, this phi n is called the Eulers function and it counts the number of prime number before n which are not prime, number before n which are co-prime to n. Right, so it is a count basically, which we have done in the previous video. Now let us see the application of this theorem and how to apply this to solve the questions. Look at the question. Use Euler theorem to find last digit of 3 to the power 30. As I have told you earlier also, last digit means mod 10 always. So when I am saying mod 10 means I am talking about dividing by 10. If I am talking about dividing by 10 means my n value is 10. And since I am looking for the power of 3, so my a value is 3. Now as per the condition of my theorem, n is greater than or equal to 1 and GCD of a and n is equal to 1. So I can apply the Euler's theorem. As per the Euler's theorem statement, a to the power phi n congruent 1 mod n. This is the statement. Now first step, I need to figure out what is the value of phi n. Right? Means I am searching for the value of phi 10. Right? Phi 10 means all numbers before 10 I will write down and I'll check how many of them are co-prime with 10. That is the count of phi. But I will not go by that method. What you have to do? What are the factors of 10? 2 into 5, both prime factors, right? So this phi n can be written as 10, that is n, 1 minus 1 by 2 and 1 minus 1 by 5. This you can check in the previous video how to find it. We have done 2-3 videos on this. Now this is 10 into 1 by 2 and into 4 by 5. Right? So 5 2s are 10, 10 cancels, so 4. So phi of 10 is equal to 4. Correct? So now I will apply the theorem. So 3 to the power 4 congruent 1 mod 10. Correct? So this is what I got the base. Now once you got the base, now you work on the question. You want to reach to 30. You are sitting at to the power 4. Right? So if you want to go to 30, let me check what number I should multiply or what power I should raise. I want to go to 30. So if I divide it by 4, so 4 7s are 28. So if I raise it to the power 7, so it will become 7 congruent 1 mod 10. So 3 to the power 28 congruent 1 mod 10. Now I want 2 more 3's, right? So I will multiply both the side by 3 square. So this will become 3 to the power 30 congruent 9 mod 10. And I can see that this 9 is less than 10. So my answer will be 9. Right? Easy? So now let us go to the next question. Find last 2 digits. 2 digits means mod 100. Mod 100 means n is equal to 100 and a is equal to 11 and both are co-prime. So I can apply the theorem. My theorem says phi n congruent 1 mod p. Okay. So mod n. Now what is phi n? Phi of 100. What are the factors of 100? 100 is equal to phi of 25 to the power 4. Right? No, not 25 to the power 4. It is 500. If I want to search, I will have the factors. The basic factor will be 2 and 5. Right? So I will have some 2 to the power r and into 5 to the power r, which will give me 100. Right? So square basically. So answer will be 100, 1 minus 1 by 2 and 1 minus 1 by 5. Correct? I need not to note down how many times 2 and 5 are repeated. 2 and 5 are the prime factor. That is more than sufficient for me. And this value is nothing but equal to 40. Right? Now, if I got 40, apply the theorem. So, 11 to the power 40 congruent 1 mod 100. Correct? Now, I am sitting at 40. I want to go to 84. So, obviously, if I square it, I'll get 80 directly. So, 80 congruent 1. This is the beauty of these theorems, whether it is Fermat or Eulers, that it is 1 this side. So I can raise it to any power. That make the calculation very easy. Now I am sitting at 80. I want to go to 84. No issues now. I can multiply it by 11 to the power 4 on both the side. Okay, mod 100. Now how to reduce this 11 to the power 4? You have calculator. I have taught you in one video how to get this. So my answer will be 41. I'll get first 441 and then again applying the mod value, I'll get the 41. Okay. Now let's move to the next question. Find remainder when 2 to the power 10 is divided by 11. So when I'm saying divided by 11 means my p value is 11. My a value is 2. Both are co-prime. So I can apply Euler's theorem. So what I need phi of 11. Correct. Now I have told you in the properties of phi in my shorts, I have told you in my video that if n is prime, then phi of n is equal to n minus 1. So this will become 10. Correct. Now apply the theorem. So a is 2. So 2 to the power 10 congruent 1 mod 10. Correct. Mod 11. Now next thing what I have to do, I got this thing. Oh, I am done actually. See, my question is so direct. 2 to the power 10 is divided by 11, then what is the remainder? So clearly here my remainder is 1 because they have given 2 to the power 10 only. If any other power means I would have moved towards that power. So this question was basically the oral question, right? Now look at this. Find remainder when 2 to the power, oh, this is a big one. Again, but method is same. I have n is equal to 11. So phi of 11 is what? 10 because 11 is a prime number. A is equal to 2. Apply the theorem. So 2 to the power I have p minus phi of n, right? What is phi of n? 10. Congruent 1 mod n. N is 11. Now from 10 to you have to reach to this number. So obviously if I multiply it by 200, raise it to the power 200, I'll get 2000. Right? And 1 raised to the power 200, it's same only. So basically what I have done, 2 to the power 10 was there. I did like this. Okay, so I got 2000. So now I'm sitting at 2000. I need 2003. So 2 cube should be multiplied on both the sides. So it will become 2003 and this will become 8. Mod 11. Correct? So what is the answer? Answer is 8. Isn't it very easy? Only you need to recognize the question and you have to check which theorem you can apply. When you do properly understand the questions can be done by the direct method also and they can be solved. If they are prime, it can be solved by Fermat theorem also and Euler's theorem also. Only you have to check the structure. Okay? So we are done with this topic. Thank you very much.